Okay, problem 7 is a proof question. Prove that the multiplicative order, ord sub n of a, divides phi of n. So this problem has a lot of our previous notation in the statement. So you need to remember, first of all, ord sub n of a is the smallest power of a, which reduces to 1 modulo n. This is a number that only makes sense for residues a that are in z mod n z cross, right? So the multiplicative units mod n. And phi of n was, well, first off, phi of n is just the number of elements in this set, which is saying that phi of n is the number of residues a which are relatively prime to n. And in this context, where we're talking about powers of a which are congruent to 1 mod n, Euler's theorem tells us that a to the power of phi of n will also reduce to 1 modulo n. So I've identified the situation where these numbers are relevant to each other. Now, the easiest way I know to prove this is by contradiction. So we know that both of these formulas are going to reduce to 1 modulo n. And since the order of a is going to be the smallest power that satisfies this equation, I know that phi of n has to be greater than or equal to order of a. So I'm going to write out and say, well, what can I do with two numbers? One is larger than the other. Well, I can attempt division. I know that phi of n is going to be equal to some multiple of the order of a plus a remainder, right? I can do this for any pair of integers, and I can stack the deck so that my remainder r is between 0 and the order of a. I need to do this because I'm trying to assess whether or not the order divides phi of n, which is going to happen exactly when r is or is not 0. So in my proof by contradiction, I'm going to say, let's assume the order of a does not divide phi of n. So in my equation here, my remainder term cannot be 0. It must be 1 or greater. That is the setup here. So what can I do with r? I can take a to the power r. I know that r is the difference between phi of n and k times the order of a. So I can say that a to this exponent is exactly the same as a to the exponent r. I don't even need to use congruences here. They're literally the same power. I can then pull things apart using the rules for exponents. A to the power phi of n minus k order of a is the same as a to the power phi of n times a to the power order of a, which is then raised to the power negative k. All right, looks good so far. Both of these terms here are actually 1 modulo n. So this is where I am using congruences. A to the power phi of n I know is 1, again, thanks to Euler. A to the power order of a is also 1. That's just what it means to be the order of a. So I've got 1 times 1, and that second 1 is raised to the power negative k, but 1 to any power is 1. So altogether, a to the power r must be 1 modulo n. The problem with this is that I now have a power of a that gives me 1 mod n, but because r is a remainder, r must be strictly less than the order of A. Here I'm using this equation. If I'm going to write things as quotient plus remainder, that remainder is going to be less than what I'm dividing by. So that contradicts the fact that order of A is the smallest power of A, which is 1 mod n. So this is the contradiction that arises from my faulty assumption. It cannot be the case that order of A doesn't divide phi of n. So actually, it must be that order of A does divide phi of n. And that is the proof.